Hi, so we are taking a look at this electrophoresis power supply. This is an ancient power supply from the 80s. It's sold by Pharmacia. Pharmacia is originally a Swedish company, and this is the high voltage power supply. It's 500 volts output at 400 milliamps, that's 200 watts. So it's used in electrophoresis process, which is basically separating large macromolecules like DNA, RNA, basically, and high electric field is applied on a medium. It could be a gel or whatever, and the particles would separate out towards the respective electrodes. So this power supply was designed roughly around maybe 1986 or 7, because most of the parts are from that age. So this is the insides of the power supply. There was a heat sink. There was a heat sink on this plane, on this side. There was a heat sink on this side, and this is the back of the power supply. So if we take a look at the front, you have selector switches for displaying voltage, current. It even detects if there is any leakage because it's a high voltage application. There's a PCB at the front, and there's a connector over here which connects to the main power board. Now this power board is actually a flyback power supply, which is very interesting because you would expect some sort of linear power supply every time you think, every time you open old equipment, but this is actually a switching mode power supply. Most of the components are from the 80s. This is the back of the unit. This is where the mains power comes in. That's standard 220 volts AC. It uses a IAC connector C13 C14 pair, and there's two fuse holders over here and one main switch. The mains connector is actually a part of a EMI filter over here. The output of the EMI filter, the two wires, live and neutral, go to two fuse holders. So both the live and the neutral is fused. The output of the fuse holder then goes to the switch. The switch is to enable and disable the unit. That then goes down into the PCB over here. Now this unit has two transformers. One is a mains transformer, which is basically just for the auxiliary supply for all of the control circuitry. So it's basically a low voltage output, and this one's a linear power supply. This is the flyback transformer, which is the main power transformer making the 500 volts output. If you look closely, you can even see the air gap in the transformer. So I shouldn't say transformer, it's a flyback power supply, so it's a coupled inductor. So this unit has one mains transformer, which is the low frequency transformer. This is used to generate the auxiliary power supply for all of the control circuit. So it's one of those seal type transformers, potted. You can still buy these, it's a very common package. After that we have a bridge rectifier, and then we have two capacitors which supplies the control circuitry. If you look closely, you can see that these capacitors have actually leaked. And that's a common failure mode in electrolytic capacitors. These are made by Roderstein from Germany, and Roderstein I think later merged with Vishay to form Vishay-Roderstein capacitors. So this is the linear power supply for the auxiliary control circuit. Taking a look at the input side, where the AC mains comes in, there's a fuse, there's an NTC to limit inrush current, then it goes to a bridge rectifier over here. This bridge rectifier is actually mounted on the side wall, which was a heatsink, which I have removed. So this forms the DC high voltage, which would be around say 330-340 volts. That gets fed to this very old Philips capacitor from 1987. You can see the date code. So this is 470 microfarads, 385 volts, and you can see these interesting bulges on the capacitor, and that's normal, that's how they used to come. And there's one more film capacitor over here, which is a REFA capacitor, and a footprint for one more cap which has not been populated. Interestingly, these caps, they have around five legs each. So this DC, the high voltage DC, then gets fed to this transistor here. This transistor is actually a NPN transistor. These days we use MOSFETs, but this is actually a NPN power switching transistor in a TO3 package. The case of this transistor itself is the collector, and the base and the emitter are available as two legs at the bottom. It's a very common package for back then. Then you can see a snubber circuit which goes across the BJT, and this is the power resistor, these are the caps, and this is the fast diode. The diode is manufactured by Philips. It's a BYW19 diode. So you can see it's a fast yet soft recovery diode. It's a 800 volt diode with less than 450 nanosecond recovery time. You could find much better these days, but I'm sure back then this was a really good choice. So in a flyback power supply, you have the main switching transistor, which builds energy in this coil. When it turns on, the current builds up in this coil, energy is stored in the core, and when you turn it off, the energy is transferred to the secondary side. So this coupled inductor is basically this large item over here. You can see it's beautifully wound, and the air gap is actually very significant. See, the air gap is necessary, otherwise when the current starts building, and if there is no gap, even though the inductance would be very high, it would instantly saturate. So if you put the air gap here, you can reduce the effective permeability, and the current could build much higher and store energy in the gap, which could later be transferred. So you can see there's two metallic posts which actually secure the transformer, and it even acts as a heat sink. The core itself connected to this plate is connected on the side, which is connected to the side heatsink wall. So it's also cooled very well. On the output of the transformer, you can see two sets of rectifiers. So the output of this flyback transformer, as you can see, goes to two diode pairs, this, and this, two pairs, and that goes to some Philips branded output capacitors. That's 22 microfarads each and 350 volt rating. The reason this is 350 volts is because this set holds about half the voltage, this set holds about half the voltage. Later they are connected in series through this network. So the final output voltage which is available at these two terminals is 500 volts. So instead of generating 500 volts in one set or one winding, they have done it in two pairs. You can also see some power resistors before they actually go to the output, 3 ohms. So if we take a look underneath the PCB to understand this power circuit, we can get a better idea. So over here you can see this is the BJT. This is the BJT snubber network, the diode and the R and the C capacitor, which then feeds, which basically drives the coupled inductor over here. The output, you can see two sets of windings with a center tap. So this is one set and this is another set. These two sets feed these capacitors, which are over here, the Philips capacitors in blue color, which then goes to the output. And if you notice, all of the traces in this PCB, they are very curvy. All of these traces, even the control circuitry traces, are very curvy. That's because this is a board made in the 80s, and back then the EDA tools did not exist. So PCBs were hand drawn like this, a very difficult process, and then they were later exposed, etched and manufactured. So at the 500 volts output, you can see this diode, a 1N5060, in this glass ball type shape. You can also see similar diodes over here. This was a common package in industrial and high reliability electronics. So if you take a look at the datasheet of the 1N5060, this is a avalanche sinterglass diode. So it's basically a sinterglass type. It's basically a sinterglass type package, and it's completely hermetically sealed. Even at high temperatures, this diode has a low reverse current. So if you look at the construction over here, These kinds of diodes are actually brazed at a temperature of greater than 600 degrees Celsius. Then they are enclosed and sealed in glass. So they are completely hermetically sealed, and these are actually very high reliability diodes. As you can see, this technique tremendously enhances mechanical strength and temperature cycling capability, increasing operating and storage temperature range while reducing thermal resistance. So it's basically a very high reliability package. In the flyback power supply, there's only one switch, which is the control switch, and in this case it's an NPN transistor. Because it's a very old power supply, MOSFETs were not so common back then. So this NPN transistor's base needs to be driven to turn it on. Turning it on will energize the winding, right? So in order to drive the base, we have a base drive circuitry. The base drive circuitry actually, you can see the traces for the base actually comes along this path. So how is the base drive achieved? So the controller IC over here, the controller IC drives these transistors, which in turn drives this transistor, and this funny looking transistor is actually a metal can package with a heat sink around it, and as you can see it sits on a base. This transistor drives this gate drive transformer. So you can see this gate drive transformer, and the core is from TDK, a very old company, and the transformer even has the Pharmacia label on it, which means it's a custom part made by TDK for Pharmacia. So this transistor, this bipolar transistor, drives the primary winding on this transformer. The secondary winding on this transformer goes via these traces through this ferrite bead and resistor into the base of the transistor. Now you can see that the gate loop, the gate path on this is extremely long. These days the gate paths on most switching converters are in just 2 centimeters, a centimeter or so. Basically it needs to be very small to minimize the ringing because there are fast switching transients. But in this case, in this old converter, this is what they have done. Probably back then proper layout guidelines and all, they had not evolved as much and they were not so common, but they have done something to reduce the ringing. You can see this is in the gate path, and it's not actually an inductor, it's a ferrite bead which acts like a lossy element at high frequencies. This will reduce the gate ringing. And funnily enough, they have used a power resistor as in the gate path. These should not be used particularly because they have coil type winding and they have inductance, so they unnecessarily cause ringing. So these are not a good choice. Nobody uses these days, but back then, probably because of the high power rating, this is all they could get. So this transistor driving this transformer drives the secondary of this transformer, and the secondary drives this gate loop over here powering the BJT. So you can see there is complete isolation in the drive circuitry. This transistor drives the primary winding, and the primary and the secondary are isolated. So the high voltage transistor is technically isolated from the control circuitry. But the feedback which comes from the output, see, the output has to be fed back so that we can sense it and regulate it. The feedback is not isolated. So technically the high voltage section and the control section is actually not isolated, because these feedback traces, as you can see, all of these feedback traces run from right from the output into the controller section over here. Isolating the output voltage from the controller is actually a very difficult process, and it would also be an expensive process because it's a DC quantity. So they found it easier just to connect it with traces. Now the voltage is obviously scaled down using resistors and so on. Then you can see two LM324 quad op amps which condition it, and then this is the main PWM controller IC. This is a TDA1060. You can see the date code is 1986. It's a very old IC, and this IC takes care of the entirety of the closed loop operation of the flyback converter. So the feedback taken is not just the output voltage, but you can see here there's something which looks like a current transformer. So it's a small E code with two windings. this large winding actually goes towards the main switching transistor over there. So the switching current flows through this, and the winding which is inside the core underneath the yellow tape actually goes to the controller IC. So what I'm guessing this is doing is measuring the primary current. So the primary peak current could be controlled. So flybacks are usually operated in current mode control. So I'm guessing this is basically what that is. But voltage feedback is also needed. So the voltage feedback should also exist. It's probably some sort of dual loop situation with a inner current outer voltage loop, but I'm not sure exactly how the controller is implemented on this. Let's take a look at the datasheet for this IC. So this is the datasheet for the TTA1060. It's a bipolar technology chip, which is basically just like the PWM controllers we use these days, like TL494, SG3525 and so on. It's just very similar to that. You can see it has the PWM outputs, it has the feedback inputs, the internal sawtooth generators, the error amplifiers. So it's a very standard PWM controller, you could say, but it's one of the earliest PWM controllers. A fun fact is that the first PWM controller was made by this person called Bob Momano. He made the first pulse width modulation controller. Before this existed, people would use other things like op amps or timer ICs like the 555 to generate the pulses. This SG1524 was one of the first IC which incorporated all of the building blocks needed to make a switching mode power supply. It had the LR amplifiers, the inner triangle wave generators and everything. And as you can see, this thing, it was made in 1975. So this is just 11 years prior to the manufacturing of most of the components used in this power supply. In case you are wondering what these parts were, these are just 7805 voltage regulators from Motorola. It's basically a part of the linear power supply, linear auxiliary power supply, which is used to power the controller section. And these are also 1986 date coded. Something interesting, over here it says Chrome Trick. This is also some Swedish technology company. I think what may have happened is Pharmacia may have contracted out the designing of this power supply to Comtrick, which is why their name is on this board, but I'm not sure. One more interesting thing, if you see this small rectifier which is used over here, the bridge rectifier over here for the auxiliary power supply, it has an international rectifier logo on it, but it says India. I wasn't aware that international rectifier actually had any sort of manufacturing in India, but if you check online, you can actually find this company called Ratan Shah International Rectifier Limited, and this company was founded back in 1969. So maybe they had partnered with International Rectifier for manufacturing of these bridge rectifiers. So it's interesting. About actually running this power supply, you can see that these caps have leaked. You can technically replace the capacitors and actually try and power it on, but I can't do that here in my workplace in case some sort of accident does happen. So I don't actually have the output characteristics. I haven't measured the output characteristics, but someone on the audio forums has, and this is what he says. It's switching at 28.5 kilohertz, and this is the output noise specs. There's a 20 volt peak to peak noise, and the high frequency noise is 4 volts peak to peak.